Hey guys, this is the lab that goes along with your inductance and inductive reactance module. Okay, so that would be page 4 of your AC Principals Lab booklet. Okay, so I'm gonna do this lab in a video form for you, just to kind of give you the highlights of what is expected for you. So I'm using a 0.2 Henry coil. Okay, so coils are rated in Henrys, okay? And I'm expected to get these different readouts from this 0.2 Henry coil. So the point of this lab is to show that AC resistance is higher than DC resistance. So initially I'm going to get my resistance reading using my multimeter across this coil, okay? And I read 2.5 ohms, okay? So I've recorded that 2.5 ohms on our chart, okay? The next information that's asked is the volts, the amps, the watts, the volt amps, the power factor and power factor angle, and all that information is given to me via my kilowatt meter, okay? So my kilowatt meter is just plugged into my bench, and then using a cheater cord, I will wire my coil and I will get all of that information and put it into the chart, and then kind of discuss what that means in regards to the expected calculations, okay? So plug that in there. Okay, so I have a hot that goes on one lead, or one connection point, my identified, and my ground. Okay, so I'm turning off my meter. I won't need it. All information will come from the readout of my kilowatt meter. Okay, so I turn it on. So in the chart, it's asking me what the voltage is across my 0.2 Henry coil, and it's giving me 117.6 volts. Okay, simple enough. It wants to know what the current draw is for this particular component, and it comes in at 0.9 amps. Okay. It wants me to indicate the amount of watts being consumed by this 0.2 Henry coil. So I just click on the watts button, and it comes up to be 7.4 watts, which I have indicated on our chart. It's asking me the volt amps, okay, the VA. There's a VA button. I press it, it's telling me 106 volt amps. And then it is asking me for the power factor. It's telling me it's 60 hertz. It's not asking that, but it's nice to know that it's reading correctly, okay? Power factor is 0.06, and I will show you how that relates to the power factor angle in just a moment, okay? So now that I have the readout information requested in the chart, I want to guide you now into the calculation part, okay? So it talks about Z coil. So Z is the impedance of the coil. So when you're dealing with AC circuits, we no longer use resistance in conjunction with Ohm's law to solve the overall current, because we are not just dealing with in-phase loads any longer. We are dealing with coils, motors. So we have to use the information and the formulas given using impedance, not resistance, okay? So it states to find the impedance of the coil, so Z coil equals, it says E coil, and I divide that by I coil, okay? So 117.6 was the voltage across the coil, and the current of the coil across the coil was 0.9, okay? So I'm gonna go 117.6 volts, divide that by 0.9 amps, and my impedance comes up to be 130.67 ohms, okay? So I'm gonna put that information here. So Z coil equals 130.67 ohms. I'm gonna take that information in a little bit, and I'm gonna build an impedance triangle with that for you, okay? So the next calculation is asking for resistance, and this is where we're gonna compare the value of resistance calculated in comparison to the DC resistance read before the circuit was energized using our multimeter. And it states that R equals P for power divided by current squared. Okay, so basically that's taking your power formula that you would have learned in first year and you're going to transpose it to find the R value, okay? So the power was given to me, and the power would be my watts, right? Power is watts, that's the unit of measurement. So I have 7.4 watts, and I'm dividing that by current squared, 0.9 squared, okay? And that gives me 9.14 ohms, okay? So resistance of the coil equals 9.14 ohms. So you can see that that's definitely a higher value than what we read through our multimeter in a disconnected component, right? And that's due to the supply being AC, right? So when we're reading across our coil with our multimeter, we are reading it from the voltage that's being supplied by the multimeter itself, which is internally fed, and it's giving you a DC voltage. So you're seeing that value of resistance coming through, but when you take the power that's generated with the current divided by the current squared, you're seeing a much higher value of resistance. And that's consistent when you're dealing with AC as opposed to DC. Okay, and then the last calculated variable they want us to get from this chart is our inductive reactance, okay? And that's a transposing of our inductive reactance or impedance formula. So Z squared minus R squared equals, so my Z squared is 130.67 squared minus my R squared, which is 9.14 squared. And just be aware that we are going to start using these formulas consistently when we get into our RLC circuits. So I don't want you to panic too much about not knowing these off the top of your head, because we haven't really used them very much at all, really. So just bear with me. This is more of an introduction to what will become much more relevant when we start doing our series in our parallel RLC circuits. Okay, and so then if I take that, it comes out to be 130.35 ohms. That is my inductive reactance. So I'm going to take that information and list it here. Okay, so it tells me in question 1 on page 6 of this lab to draw an impedance triangle for the coil. Okay, so that's why I wrote this information down here. So I'm going to erase that and draw an impedance triangle. So this is an introduction to the triangle. The triangle method becomes very important in solving the series and parallel RLC circuits, which is a very big component of second period. Okay, so impedance triangle. So I have a right angle triangle, and each side of the right angle triangle represents one of these variables that we just calculated, okay? So the bottom part of your impedance triangle represents the in-phase part of the load. So when you're dealing with a coil, you are dealing with a part resistance, part inductance. So what is a coil? A coil is many turns of copper wire. That coil has a small variable of resistance in it. When we talk about pure inductors, that is theoretical. It is not realistic to have a completely pure inductor because it's constructed of copper, and copper has an element of resistance. So I'm drawing my symbol to represent that. So my coil has a part of resistance, and that is known as RC. So resistance of the coil, and that is 9.14 ohms, okay? Then I have the inductive part of the coil, and that would be the component of the coil that creates inductive reactance, which is a part of the opposition of current flow. So the coil part of the inductor, I'm drawing like that, and I'm labeling it XL, and that is 130.35 ohms, okay? So that is the information that we calculated based on the information that we measured using our kilowatt meter. So how do I relate that to an impedance triangle? So the resistance of the coil is considered my in-phase portion of my coil. That is going to be the base of my right angle triangle, which if you think about your quadrants and your phasors, the bottom part of your triangles is your 0 degrees. So in-phase loads occur and are at reference of 0 degrees. So R of the coil equals 9.14 ohms. Okay, so that is the bottom of my right angle triangle, and it represents the in-phase portion of my inductor. The inductive reactance part of my coil would be at 90 degrees. And let's have a look at that. XL equals 130.35 ohms. So we talked about how current is affected by inductance, and that's shown in its relationship between the current and the voltage in the circuit. What does current do in reference to voltage in the inductive portion of our coil? Well, that goes back to our ELI-ICE acronym. And again, this is like an introduction to something that we are going to be working on a lot in the future. So ELI is the part that we would use to demonstrate the relationship between current and voltage in an inductive circuit. L representing inductive. Our current is lagging our voltage, right? So in a inductive circuit, current, so in the inductive circuit portion, current lags voltage by 90 degrees, which is indicated in its position on the right angle triangle. So my resistive portion of my coil is considered in phase at 0 degrees. Hopefully this is still recording as my, yep, it is, okay, because I'm losing battery here. So my in-phase portion is at 0 degrees. That means in phase, so current and voltage, their relationship are rising and falling in sync with each other at the same time, at the same rate. The inductive reactance portion, ELI is our acronym. Inductive portion, current is lagging our voltage by 90 degrees, and that's indicated by its position on the impedance triangle. 90 degrees, it's 90 degrees out of phase with our resistive portion. And then if you were to do Pythagorean on those two sides, you would equal our impedance value, which we indicated by going voltage divided by current, okay? So I'm gonna use 9.14 squared plus 130.35 squared equals 130.67, right on the nose. Impedance of the coil equals 130.67 ohms. The impedance value is the vectorial sum of my in phase and my inductive portion of my 90 degrees out of phase portion. So I'm adding these two sides vectorially to give me my overall impedance, and my overall impedance is my total opposition to current flow in this inductive resistive AC circuit. Simple, right? Okay, so what is the angle of opposition for the coil, which is the second part? Okay, so to find the angle theta here, what would we do? So I have all three sides in reference to angle theta. This is going to be I'm going to use a different color, my opposite side, my adjacent side, and my hypotenuse side, okay? So I'm going to use cosine because cosine becomes the trig function that we will use all the time when we're looking for the power factor of our circuit. So if you're not sure of what cosine is, you're going to write down your SOHCAHTOA acronym. Okay, cosine is adjacent over hypotenuse. Okay, which is my adjacent is 9.14 0.14, divide that by 130.67 ohms, okay? I punch that into my calculator. Hopefully we read similar to what we measured. We read power factor. Cosine is your power factor. We read that to be 0.06 lag. So I'm just going to confirm that with my calculation. So 9.14 divided by 130.67 equals 0.069. Okay, and if I inverse cosine that, that'll allow me to find the angle of opposition for the coil. Second function cos, or cos to the -1, that gives me an angle of 85.99 degrees. Okay, so like I said, this is just an introduction to some of the variables and things that we will be expected to calculate when we start dealing with inductors in series with resistive loads, inductors in parallel with resistive loads. So this is just a little bit of an introduction to what's expected. The point of this lab was to confirm that your AC resistance is much higher than your DC, which we have done. Thank you.